use them every day to pack our lunches, store leftovers, or deliver takeout. Plastic food containers are everywhere, but what if we told you some of them were made from yesterday's trash? That soda bottle you threw away last month, it might be holding salad today. In this episode, we go behind the scenes to uncover how discarded plastic, once destined for landfills or oceans, is collected, purified, melted down, and reshaped into safe, durable containers fit for your fridge and your microwave. From curbside bins to cutting-edge machines, and from dirty waste to food-grade clean, it's a journey of transformation that combines recycling, chemistry, and precision engineering. This is more than just plastic, it's a second chance. Welcome to How It's Made, Recycled Plastic Food Containers. The journey of a recycled plastic food container starts long before it reaches the factory. It begins at the curbside. Across neighborhoods, cities, and commercial zones, used plastic bottles, food packaging, and containers are dropped into recycling bins. These items are then transported to regional materials recovery facilities, where the transformation begins. Upon arrival, the plastic waste is unloaded in massive piles and pushed onto conveyor belts. The first round of sorting is mechanical. Large spinning drums separate light materials like film plastics from heavier objects. Magnets pull out any stray metals. Then comes the key step, optical sorting. High-speed infrared scanners detect the type of plastic based on how each piece reflects light. Once identified, powerful air jets separate PE, polyethylene terephthalate, from PP, polypropylene, and so on. These are the two most commonly recycled plastics used for food containers. Manual workers follow, picking out non-recyclables, dirty items, or anything that could contaminate the batch, like greasy pizza boxes or foil. The selected plastic is then grouped by polymer type, color, and grade, and moved into separate holding bays. Any container that once held chemicals, paint, or hazardous material is discarded, because only the cleanest feedstock can become food safe again. Once sorted, the plastic heads for a thorough washing and shredding process. But even at this early stage, the path from trash to table has already begun. Once the plastic has been sorted by type and quality, it moves into the next phase, transformation. Large conveyor belts carry the selected plastic into a granulator, an industrial shredder with sharp rotating blades that pulverize bottles, trays, and containers into small flakes, each about the size of a fingernail. This process dramatically increases surface area, making the next steps more efficient. But before these flakes can be remade into food-grade containers, they must be spotlessly clean. Shredded plastic enters a friction washer, where high-speed paddles agitate the flakes in a mixture of hot water and biodegradable detergent. This removes any residual food, labels, glue, and surface oils. Now that the plastic flakes are clean, dry, and sorted, it's time to turn them into something new. Plastic pellets, the building blocks of nearly every plastic product made today. The flakes are fed into a twin-screw extruder, a long cylindrical machine that both heats and mixes the material. Inside, giant rotating screws push the flakes forward while raising the temperature to over 250 degrees 482 degrees Fahrenheit, hot enough to melt plastic, but not to degrade it. As the plastic becomes molten, it's forced through fine mesh filter screens that remove any remaining microcontaminants, like tiny bits of paper, glue, or metal. The pressure and filtering here are critical. One flaw could compromise an entire batch of food-grade product. The filtered plastic then exits the extruder in long, thin strands, often called spaghetti. These strands pass through a cooling water bath, solidifying as they travel along a moving belt. At the end of the line, a high-speed rotating blade cutter chops the cooled strands into uniform pellets, each no larger than a grain of rice. These pellets are then dried and conveyed into storage silos or packed into bags for transport. Each batch is sampled and tested for molecular weight, melting point, and impurity levels. Only pellets that pass these strict quality controls will be approved for use in food contact manufacturing. These tiny pellets are now ready to be reborn as packaging that protects, preserves, and serves. Next up, sheet extrusion, turning pellets into plastic sheets. With clean, uniform pellets now ready, the next step is to transform them into flat plastic sheets, the foundational material for making food containers. The recycled pellets are poured into the hopper of a sheet extrusion machine, essentially a larger, wider version of the extruder seen earlier. Inside, the pellets are heated once again to their melting point, typically between 220 to 260 Celsius, depending on the polymer type. With plastic sheets now cooled and rolled, it's time to turn flat material into a three-dimensional product, a food container you can actually use. The rolls are fed into a thermoforming machine, a precise system that combines heat, pressure, and vacuum to shape the plastic. First, the sheet is unrolled and passed through heating zones, where it's gently warmed to just below its melting point, enough to soften, but not to form. Once pliable, the sheet advances over a forming station, where it's pressed into molds representing the final shape: clamshell containers, deli trays, salad bowls, or custom designs. A combination of vacuum suction and compressed air pulls the sheet tightly into every contour of the mold, ensuring consistent wall thickness and structural integrity. This process can form dozens of containers per second, depending on the mold configuration. After shaping, the sheet moves to the cutting station, where sharp dies punch each container out of the surrounding excess material, known as skeleton trim. But nothing is wasted. The leftover plastic is immediately shredded and refed into the extrusion system, creating a closed-loop process that dramatically reduces material loss. At this stage, optional features like recycling codes, company logos, or custom textures can be embossed directly into the container surface. The formed containers are then stacked, counted, and conveyed for final sterilization, the last step before they're ready to hold real food. Before recycled containers can touch anything edible, they must meet one final standard: absolute cleanliness and safety. Freshly molded containers enter a UV sterilization tunnel where powerful ultraviolet light eliminates bacteria, viruses, and mold spores without using chemicals. For certain applications, steam sterilization is used instead, ensuring containers meet both FDA and EU food contact regulations. Next, robotic arms perform visual inspections, using high-resolution cameras to detect cracks, warping, or surface defects. Sensors also verify wall thickness and sealing tolerance. A random sampling of each production batch is subjected to stress testing, including compression, drop impact, and temperature resistance, simulating real-world handling from freezer to microwave. Only the containers that pass all criteria move forward. Those that don't are recycled back into the process. Clean, strong, reliable. These trays are now ready for packing, distribution, and their second life in your hands. From curbside bins to conveyor belts, from plastic flakes to polished trays, the journey of a recycled plastic food container is one of transformation, precision, and purpose. What began as discarded waste has now become something clean, safe, and useful. And thanks to modern recycling technologies, it can go through this cycle again and again. Each container represents more than just packaging. It's a commitment to circular thinking, to using what we have smarter, to reducing waste without sacrificing performance, and to reminding ourselves that every small decision, even what we throw away, can shape what comes next. In a world full of disposables, this is what renewal looks like. If you enjoyed this journey from trash to table, don't forget to like, subscribe, and tap the bell icon to explore more stories behind the things we use every day. There's always more to discover, right here on How It's Made. Every year, billions of tires reach the end of their life. Piled in landfills or abandoned in open fields, they pose a serious environmental challenge. Tires are non-biodegradable, highly flammable, and extremely difficult to dispose of safely. what if these old tires could be transformed from a problem into a powerful solution? Welcome to the world of modern tire recycling plants, where discarded rubber is turned into energy and material for one of the world's most essential building products, cement. In this documentary, we'll take you behind the scenes of an advanced facility that converts waste tires into valuable fuel and raw material for cement production. From collection to combustion, from steel separation to clinker creation, this is the incredible journey of old tires on their way to becoming part of the foundations of our cities. The scale of the challenge is staggering. Each year, the world discards more than 1.5 billion tires. That's over 25 million tons of rubber waste, enough to circle the planet nearly 200 times if laid end to end. Unlike many other forms of waste, tires are especially problematic. Their rubber is reinforced with steel and synthetic fibers, making them durable but difficult to break down. Left in landfills, they trap water and become breeding grounds for mosquitoes. And when they catch fire, they burn for weeks, releasing toxic smoke. For decades, the question remained, what do we do with old tires? The answer increasingly comes from the cement industry. Cement kilns, with their extremely high operating temperatures, provide an ideal solution for using old tires as alternative fuel and raw material. The process begins long before the tires arrive at the plant. Across cities and highways, used tires are collected from auto shops, recycling centers, and municipal programs. Trucks, specially designed for heavy loads, transport thousands of worn-out tires each day to regional tire recycling plants. Before entering the facility, the tires are inspected and weighed. Records ensure full traceability, from the moment a tire leaves a car repair shop to its final transformation in the kiln. Once inside, the tires face their first major transformation, shredding. Giant industrial shredders, equipped with hardened steel blades, slice the tires into smaller pieces called tire chips. Each chip is typically 2 to 4 inches across. This size makes them easier to handle, feed, and burn in cement kilns. As the tires are shredded, magnets pull out the steel wires embedded within the rubber. These wires, which once reinforced the tires on the road, are collected separately and sent for recycling in steel mills. This step ensures that only clean rubber chips move forward. The shred tire chips now look nothing like the original products. They're lighter, easier to transport inside the plant, and ready for the next stage, energy recovery. At the heart of the process lies the cement kiln, a massive, rotating cylinder that stretches up to 200 meters in length and operates at temperatures exceeding 1,400 degrees Celsius, 2,552 degrees Fahrenheit. Tire chips are introduced into the kiln as a secondary fuel. Their high calorific value makes them an excellent substitute for coal or petroleum coke. In fact, 1 ton of tires provides about the same amount of energy as 1 ton of high-quality coal. Feeding systems precisely control how many chips enter the kiln each minute. Too few, and the kiln temperature may drop. Too many, and combustion becomes unstable. Operators monitor every detail using advanced sensors and control rooms that track the process in real time. As the tire chips ignite, the intense heat breaks them down completely. The rubber vaporizes, releasing energy that fuels the chemical reactions inside the kiln. Unlike in open fires, this combustion occurs in a controlled, oxygen-rich environment, ensuring near-total destruction of harmful compounds. The steel that wasn't removed earlier melts and integrates into the raw materials, contributing essential iron to the clinker formation. The ash from the rubber becomes part of the mineral matrix of the cement. In this way, 100% of the tire material is put to use. Energy, minerals, and even steel all contribute to the production process. Inside the kiln, limestone, clay, and other raw materials react under the heat powered in part by the tires. The result is clinker, the gray nodules that form the base of Portland cement. Clinker leaves the kiln glowing red hot, then passes through powerful coolers. Fans blast air at high speed to rapidly reduce its temperature, preserving the crystal structure necessary for strength and durability. These clinker nodules are then ground into the fine powder we recognize as cement. The use of old tires in cement production offers multiple environmental benefits. Reduced fossil fuel use. Every ton of tires burned replaces nearly a ton of coal. Lower carbon emissions. Controlled combustion in kilns reduces overall greenhouse gas output compared to landfill or open burning. Waste reduction. Millions of tires avoid landfills each year, easing pressure on limited disposal sites. Material recovery. Steel and ash from the tires contribute to cement chemistry, leaving virtually no residue. Studies show that using tires as alternative fuel can reduce the cement industry's fossil fuel consumption by up to 20%, a major step towards sustainability. Of course, such a powerful process demands strict safety and quality measures. Workers wear protective gear, and automated systems handle the most dangerous tasks, reducing human exposure. Laboratories on site regularly test both clinker and emissions to ensure compliance with environmental standards. Modern kilns are equipped with advanced filters and scrubbers to capture any remaining pollutants, ensuring clean air for surrounding communities. By transforming old tires into energy and raw material, tire recycling plants embody the principles of the circular economy. Instead of viewing tires as waste, we see them as resources waiting for a second life. The cement industry's use of waste tires is expanding worldwide, turning a global problem into a vital solution. What was once a symbol of pollution now becomes part of the foundations of our cities, bridges, and roads. If you enjoyed discovering how old tires are transformed into cement, don't forget to subscribe and hit the bell icon. We bring you more amazing behind-the-scenes stories of technology, recycling, and innovation every week. Subscribe now and be part of our journey toward a cleaner, smarter, and more sustainable world. Every year, the world discards hundreds of millions of smartphones, each filled with tiny components that are no longer useful to us, but hold an unexpected treasure. Inside these outdated devices lies gold, not metaphorically, literally. Microscopic traces of the precious metal coat circuit boards, connectors, and chips, giving us an opportunity to extract incredible value from what we usually throw away. In fact, 1 ton of used mobile phones contains more gold than 1 ton of mined gold ore. But how do we recover it? What kind of technology, precision, and chemistry are involved in turning tech trash into 24-karat treasure? Today, we step inside a high-tech recycling facility where discarded mobile phones undergo a meticulous process to extract pure gold, using chemistry, fire, and cutting-edge machinery. This is industrial recycling at its most precise and valuable. This is how 24K gold is made from e-waste. Our journey begins at a centralized e-waste collection hub, where discarded electronics from around the country are gathered. From urban drop-off programs and corporate tech recycling to bulk shipments from phone retailers, the waste arrives in containers, stacked high with smartphones, tablets, and other compact electronic devices. Each of these devices contains minute quantities of precious metals, but first, they must be sorted. Workers at the sorting facility wear protective gear and begin the initial separation process. The outer plastic casings are removed, and lithium batteries are extracted to be handled separately due to fire and explosion risks. The real prize lies inside, the printed circuit boards, or PCBs. These are the green or blue slabs that house microchips, capacitors, and gold-plated connectors. Each PCB contains a fraction of a gram of gold, but when you have thousands of boards, the numbers add up fast. Circuit boards are collected into large plastic bins, while other parts, screens, plastic, and aluminum, are sorted for their own recycling streams. The PCBs are loaded onto a conveyor belt that feeds them toward the material reduction phase. But before they get shredded, any remaining components, such as glass chips or magnetic drives, are removed. This ensures a clean feed and helps prevent contamination in the later chemical stages. This pre-sorting stage is both manual and mechanical. While human workers perform delicate separation tasks, larger mechanical arms and automated trays assist with bulk movement and categorization. Every single action is documented and logged, not only for quality assurance, but for environmental regulation and traceability. This gold extraction process is highly controlled, as it involves both valuable materials and hazardous waste. With the non-essential parts removed and the boards carefully sorted, we now move to the next stage, grinding them down into something far more manageable. Once the printed circuit boards have been sorted and stripped of hazardous parts, they enter the second phase, shredding and material reduction. The goal here is simple: transform bulky boards into fine particles, increasing surface area and making it easier to separate metals later on. The conveyor belt feeds the PCBs into an industrial shredder. This massive machine is fitted with rotating steel blades capable of pulverizing hardened materials. Within seconds, circuit boards are reduced to tiny fragments no larger than a grain of rice. The resulting material, often called e-scrap granulate, is collected in large bins. But this mix isn't just gold. It's a chaotic blend of metals, resins, fiberglass, and microscopic dust. Now it's time to separate the components. First comes magnetic separation. A spinning drum lined with magnets pulls out any ferrous materials, such as leftover screws or steel connectors that survived the shredding process. Next is the eddy current separator. This high-speed rotating system uses magnetic fields to eject non-ferrous metals like aluminum and copper from the conveyor stream. These lighter metals are pushed into separate bins for recycling. What remains is the real target, a high-density mix of non-magnetic materials including gold, silver, palladium, and platinum, all still attached to fiberglass and resin dust. The dust is passed through vibrating screens and cyclone separators, which sort particles by size and density. Larger chunks are re-shredded, finer, more homogeneous particles move forward. Throughout this process, powerful vacuum systems remove harmful airborne particles, sending them through activated carbon filters to trap toxins. Safety and environmental compliance are paramount. After all, this isn't just valuable, it's volatile. By the end of this stage, the factory is left with bags of fine powder, black, gray, and occasionally speckled with metallic glints. Hidden in this unassuming dust is the gold we're after. But separating it from the rest of the material isn't just a matter of filtering. It requires precision chemistry and one of the most powerful reagents in modern metallurgy. The shredded circuit board powder is now ready for the heart of the operation, chemical extraction. And the star of this phase is one of the most powerful reagents known in metallurgy, aqua regia. Aqua regia, meaning royal water in Latin, is a highly corrosive mixture of nitric acid and hydrochloric acid, typically in a 1:3 ratio. This golden yellow solution has a unique ability. It can dissolve gold, a metal resistant to most acids. In sealed chemical reactors, the fine e-waste powder is carefully mixed with the freshly prepared aqua regia. The tanks are made of reinforced materials resistant to corrosion, and the process is fully enclosed to protect both workers and the environment. As the acid mixture is poured in, a chemical reaction begins. Fumes of nitrogen dioxide and chlorine gas rise from the tanks. Industrial ventilation systems quickly capture and neutralize these gases in scrubbers before they reach the outside air. Over the course of several hours, the acids work their way through the powder, breaking molecular bonds and dissolving the gold into a solution of gold-3 chloride, also known as chloroauric acid. This solution takes on a bright orange hue, a visual confirmation that gold is now in liquid form. Once the reaction is complete, the mixture is filtered to remove undissolved materials, such as plastic fibers, ceramic particles, and non-precious metals. These solids are safely disposed of or sent for further recycling. Now comes the delicate process of recovering gold from the liquid. To do this, workers add a reducing agent to the gold-rich solution. The most commonly used is sodium metabosulfite. a white crystalline powder. As the reducing agent is added, the solution begins to react. Tiny particles of gold start to precipitate out of the liquid. At first, it looks like fine brown dust settling to the bottom of the tank. But under a microscope, this brown sludge reveals its true nature. Microscopic flakes of gold, some as small as 1 micron across. These flakes cluster together to form what is known in the industry as gold mud. The gold mud is collected, washed with water and diluted acid to remove any remaining chemicals, and then dried in industrial ovens. At this point, it contains over 95% gold by weight, but it's still not pure. The next step, refining and smelting, will take this muddy powder and transform it into glittering bars of 24-karat gold. But before we move on, it's worth noting, the aqua regia process is effective, but dangerous. Strict protocols, chemical handling standards, and environmental safeguards must be in place to prevent accidents or contamination. This is not backyard chemistry, it's industrial science. And it's what makes gold recycling for mobile phones not just possible, but incredibly efficient. With the gold mud fully dried, the next step is turning this powdery residue into solid, gleaming gold. This process is known as smelting, the moment where science meets fire. First, the gold mud is weighed and placed into a high-temperature induction furnace. These furnaces can reach temperatures above 1,100 degrees Celsius, 2,012 Kelvin, more than enough to melt gold, which liquefies at 1,064 degrees Celsius. Inside the crucible, fluxes, chemical compounds such as borax and silica, are added to help bind with impurities. As the mixture heats, unwanted elements separate and rise to the surface as slag, which is carefully skimmed away. What remains is molten gold, glowing with an unmistakable orange-red light. The liquid metal is then poured into graphite molds, rectangular, heat-resistant containers designed to shape and cool the gold uniformly. Within minutes, the metal solidifies. The bars are removed from the molds and immediately inspected for defects. Each ingot is then cleaned and tested using X-ray fluorescence, XRF spectrometry, which verifies the gold's purity. The gold is clear, 24-karat gold, 99.99% pure. These bars might only weigh a few hundred grams each, but they represent the successful recovery of gold from thousands of mobile phones. Their journey from e-waste to bullion is almost complete. Next, they'll be stamped, logged, and either stored securely or re-entered into the global supply chain. Once the gold bar is confirmed to be 99.99% pure, they are logged and labeled with a unique serial number, weight, and purity rating. These details are stored in a centralized digital registry, allowing for full traceability from e-waste origin to final gold product. Security is a top priority. The finished bars are stored in vaults with biometric access, 24/7 surveillance, and reinforced steel doors. Some are retained as inventory, while others are shipped to buyers across the globe. These buyers vary. Jewelry manufacturers often purchase recycled gold to produce high-end rings, bracelets, and luxury watches. Electronics companies reuse the gold for semiconductors, connectors, and microprocessors, particularly for medical devices and aerospace components where conductivity and corrosion resistance are critical. In some cases, the gold is refined even further into gold leaf, nanogold, or specialty chemical forms used in scientific research. What's fascinating is how this gold, once embedded in old smartphones, is reintroduced into the very industries it came from. It's a closed-loop system, where discarded technology becomes raw material for new innovation. Each gold bar is more than just a store of value. It represents a victory of resource recovery over waste, and a powerful example of how materials can live many lives when processed responsibly. Electronic waste is one of the fastest-growing waste streams in the world. Every year, we generate more than 50 million metric tons of e-waste, much of it ending up in landfills, leaking toxic substances into the environment. Gold recycling offers a powerful alternative. Traditional gold mining is energy-intensive and environmentally destructive. To produce just one gold ring, up to 20 tons of rock may be mined, crushed, and chemically treated, often involving cyanide or mercury. It also consumes vast amounts of water and disrupts ecosystems. In contrast, urban mining, recovering gold from discarded electronics, uses far less energy and generates significantly less waste. It doesn't destroy landscapes or pollute rivers. Instead, it recovers precious metals that already exist in circulation. Recycling also supports circular economy principles, minimizing resource extraction, maximizing reuse, and designing products with end-of-life recovery in mind. Companies involved in electronic recycling are now working to improve efficiency, reduce the use of hazardous chemicals, and expand collection programs globally. Consumers play a role too. By properly disposing of old electronics, we help ensure these valuable resources can be recovered instead of wasted. In the end, gold recycling isn't just about value, it's about responsibility. It's a sustainable model that protects both the environment and the economy. From forgotten drawers to factory floors, from shattered smartphones to gleaming gold bars, the journey of electronic gold is one of transformation. Every step in the process, collection, shredding, chemical extraction, purification, demonstrates the power of modern technology to reclaim value from what we once considered trash. This isn't just recycling, it's industrial alchemy, a practice that turns the waste of yesterday into the resources of tomorrow. And it reminds us that hidden inside our devices are materials with lasting worth, if we know how to retrieve them. Next time you upgrade your phone, think of the tiny traces of gold inside. Know that with the right hands and the right process, that gold doesn't have to be lost. It can be recovered, reused, and reborn.
We take scrap material, we melt it down, then we send it through the rolling mill and we make rebar and we make T-post and then we ship it out.
Tell them, hey, mommy has a really good career.
We generated over and over again, and we just keep, we're a mini mill, we have some micro mills.
Bridges, buildings, any kind of roads. The new Texas Ranger Stadium all has our rebar.
Family, Steel, Texas that retired from there. My grandpa retired from there. I have an uncle in Steel, Arizona. It's in the blood, you know, I like it, I love it.
CMC always recognizes hard work.
Every day, mountains of scrap metal are tossed aside. Forgotten relics of old cars, demolished buildings, and decommissioned machines. But what if we told you these discarded metals are being reborn as one of the most essential materials in modern construction? Welcome to the world of rebar, steel reinforcement bars that form the invisible skeleton of buildings, bridges, and highways. And in this video, we're taking you inside an eco-friendly steel factory to see how tons of scrap metal are transformed into high-strength rebar, ready to support the weight of the modern world. Stay tuned to discover the incredible journey from junkyard to construction site. Steel is the most recycled material on Earth. In fact, over 70% of rebar in the US is made from recycled scrap metal. And that's not just good economics, it's a sustainability win. At the heart of this transformation is a type of facility known as an electric arc furnace, EAF steel mill. Unlike traditional blast furnaces, EAFs don't rely on iron ore or coal. Instead, they use electricity to melt down existing steel, cutting carbon emissions by as much as 75%. In this video, we visit Greenform Metals, one located of the most advanced, eco-friendly steel plants in the world, just outside of Houston, Texas. The journey begins at the scrapyard. Each day, truckloads of ferrous scrap arrive at the factory. This includes shredded car bodies, demolition debris, steel beams, industrial cast-offs. A crane equipped with an electromagnetic claw lifts the material and sorts it, removing non-ferrous metals and contaminants. The selected steel is then sent to a pre-processing area, where it's shredded and sized to ensure consistent melt quality. Once sorted, the scrap is carefully weighed and conveyed to the furnace loading area. Now comes the heart of the process, the electric arc furnace. This massive vessel is lined with heat-resistant bricks and equipped with graphite electrodes that can generate temperatures over 3,000 Fahrenheit, 1,650 degrees. As the electrodes lower into the furnace, a powerful electric arc forms, creating a plasma field that melts the scrap metal in minutes. This process is not only fast, it's efficient. Thanks to renewable electricity sources like solar and wind, greenform metals achieves near zero carbon emissions during melting. Once melted, the liquid steel, called molten metal, is tapped into a giant ladle and transported to the next phase. But raw molten metal isn't ready to become rebar just yet. It needs refining. The ladle enters the ladle metallurgy furnace, LMF, where engineers fine-tune the chemistry of the steel. By adding small amounts of carbon, manganese, and vanadium, they adjust the strength and ductility. Impurities like sulfur and phosphorus are removed using fluxes. The process is closely monitored by metallurgists who take regular samples to ensure the steel meets strict ASTM standards for rebar. Once the composition is perfect, the steel is ready to solidify. Next up, continuous casting. Molten steel is poured into a mold that quickly cools it into a semi-solid shape, typically a square billet about 6 to 8 inches wide. The billet then travels through a series of rollers and water sprays to fully solidify while maintaining its shape. This continuous casting method is faster and more efficient than traditional ingot casting, with virtually no waste. The red-hot bills are then cut to length and sent to the reheat furnace for the final forming stage. This is where the transformation really takes shape. The bills re-enter a reheat furnace to bring them back to a pliable temperature. From there, they're fed through a series of rolling stands that progressively shape them into long, slender rods, each one with a ribbed surface to help concrete grip the steel. The ribs are not just aesthetic, they're engineered for maximum adhesion in concrete. Depending on the final use, the rebar is rolled into different diameters, typically ranging from 3/8 inch to number 18, 2.257 inch. The rods are then cut to standard lengths, usually 20 or 40 feet, and moved to the cooling bed. Before any rebar leaves the plant, it undergoes a series of rigorous tests. Each batch is sampled and checked for tensile strength, bendability, chemical composition, corrosion resistance. Only when it passes all quality control metrics is the rebar certified and stamped with a unique mill code, allowing for full traceability from melt to shipment. Once cooled and inspected, the rebar is bundled, tagged, and stored in massive outdoor yards. From here, it's loaded onto trucks or rail cars and sent across the country to skyscraper projects in New York, bridge repairs in California, and new housing developments in the Midwest. Each bundle represents not just a batch of steel, but a triumph of recycling, engineering, and environmental innovation. As the world races to decarbonize, industries like construction and steelmaking must evolve. And facilities like Greenform Metals are leading the way. By recycling scrap, using clean electricity, and deploying smart automation, they prove that heavy industry doesn't have to be heavy on the planet. In fact, every ton of recycled steel used saves 1,400 pounds of iron ore, 2,400 pounds of coal, 120 pounds of limestone, and reduces greenhouse gas emissions by nearly 60% compared to virgin steel production. Thanks for watching. If you enjoyed this deep dive into the world of steel recycling, don't forget to like, subscribe, and check out our next video, where we go inside a factory turning waste plastic into highway asphalt. In a handful of modern recycling factories across the US, broken bottles, shattered windows, and piles of glass waste are getting a brand new life as colorful, durable tiles for homes, offices, and even luxury hotels. In today's video, we're going to take you inside one of these factories and show you exactly how trash becomes treasure. From the moment the glass arrives to the moment the finished tiles are packed and shipped, you'll see every step in the journey. And trust me, it's way more fascinating than you think. Before we jump in, if you love discovering how everyday things are made and how waste can be turned into something amazing, go ahead and hit that subscribe button and turn on the bell. We post fascinating behind-the-scenes stories every week, and you don't want to miss what's coming next. All right, let's head inside the factory. It all starts with mountains of glass waste. Every single day, trucks pull up to the factory loaded with recycling bins, giant bags from construction sites, and crates from municipal collection programs. This isn't just beer bottles and soda jars, it's everything. Old mirrors, cracked windshields, broken tabletops, even glass from demolished buildings. If it's glass, it can be recycled. At the gate, every load is weighed. The weight, the source, and the type of glass are recorded. That way, the factory can track exactly where each batch came from. It's like keeping a paper trail, but for glass. Here's the thing about glass waste, it's never just glass. You've got bottle caps, plastic labels, bits of ceramic, maybe even a stray fork or two. All of that has to go. So the first stop is the sorting line. Workers stand along fast-moving conveyor belts, pulling out big contaminants by hand. Anything that could jam the machines or ruin the tiles. Next, the glass passes through high-tech separators. Air jets blow away lightweight trash like labels and paper. Magnets remove any metal, like jar lids or steel bottle rings. Screens and sifters shake out small stones or dirt. Then comes the washing stage. Imagine a giant industrial dishwasher. Jets of water blast away leftover liquids, sticky soda residue, and fine dust. After this bath, the glass sparkles. Some factories sort glass by color at this point: clear, green, amber, because it makes it easier to control the final tile color. Others keep it all mixed for a more speckled mosaic look. Now the clean glass heads to the crusher. This thing is a beast. Huge spinning hammers smash the glass into small chunks called cullet. If you've ever dropped a glass and seen it break into thousands of tiny pieces, this is the same idea, except controlled and consistent. The pieces are usually between the size of a pea and coarse sand. Why crush it? 2 reasons. 1, smaller pieces melt more evenly later in the kiln. 2, it's easier to mix with other ingredients when it's fine. The finer the glass, the smoother the final tile surface will be. For some designs, they even grind it to a powder so fine it feels like flour. Crushed glass alone can't hold the shape of a tile. It needs a glue to bind it together. This is where binders and additives come in. The cullet goes into massive mixing drums, along with clay or porcelain powder, gives the tile strength and structure. Pigments, or color. Want a bright cobalt blue kitchen backsplash? That's thanks to a pinch of mineral pigment. Fluxing agents. These lower the melting point of glass so the factory can save energy when firing. The recipe is like baking cookies. A little too much of one ingredient and the whole batch turns out wrong. Technicians carefully measure each component to make sure every tile looks and performs exactly the same. Once mixed, the material feels a bit like damp beach sand, gritty but moldable. Here's where the transformation starts to get exciting. The glass mixture is fed into tile presses, huge machines that slam down with tons of pressure, squeezing the mix into perfectly flat, square shapes. These presses can pump out hundreds of tiles per hour. For more artistic or decorative tiles, the mixture is poured into molds instead. Some designs even sprinkle in bigger chunks of colored glass at this stage, so when the tile is fired, you get gorgeous jewel-like specks inside. When they come out of the press or mold, the tiles look, well, kind of dull. They're just pale, chalky shapes. But that's about to change in the kiln. Freshly shaped tiles are still damp from the mixing process. If you put them straight into a hot kiln, they'd crack from the steam pressure. So they go into drying chambers, long, warm tunnels where hot air gently removes the moisture. This can take anywhere from a few hours to overnight, depending on the tile size. By the time they leave, the tiles are completely dry and ready for the big heat. The firing stage is where these lifeless chunks of glass and clay turn into something you'd actually want on your kitchen wall. The tiles are loaded into tunnel kilns, basically giant ovens the length of a city bus. Slowly, they move through zones that get hotter and hotter until the temperature reaches between 1,500 degrees and 2,200 degrees Fahrenheit, about 800 to 200 degrees Celsius. At these temperatures, the glass particles soften and fuse together into a solid mass. Pigments wake up, revealing their final, vibrant colors. Any larger decorative chunks melt just enough to bond with the rest, creating smooth, glassy patterns. The factory controls the firing time and temperature down to the minute. Go too hot, and you lose the color. Too cool, and the tile stays brittle. When the tiles leave the hot zone, they can't just be dumped into room air, they'd shatter from thermal shock. Instead, they pass through an annealing section, where the temperature drops slowly over several hours. This gradual cooling relieves internal stress, making the tiles much stronger. By the end of this stage, they're cool enough to handle, and they look completely different from when they went in. Smooth, colorful, and solid. Some tiles go straight to packaging, but many get extra treatment to make them even more beautiful or practical. Polishing for a glossy, mirror-like finish, texturing for slip-resistant surfaces, perfect for bathroom floors, glazing to add shine, depth, or patterns. The finishing line is where tiles really show their personality. It's also where quality inspectors check for chips, cracks, or color issues. Anything less than perfect gets recycled back into the process. Finally, the good tiles are stacked into cardboard boxes, cushioned to prevent damage, and labeled with size, color, and batch number. The boxes are loaded onto pallets, shrink-wrapped, and rolled onto trucks. Some will head to local home improvement stores, others to high-end designers or export markets. From here, they'll be installed in kitchens, hotel lobbies, swimming pools, anywhere a beautiful, durable tile is needed. It's proof that with the right technology and a little creativity, even broken trash can be turned into something beautiful and lasting. And that's the incredible journey of how broken glass gets a second life as beautiful, durable tiles. If you enjoyed this behind-the-scenes look and want to see more amazing transformations like this, make sure to subscribe and tap the bell icon so you never miss a new video. Thanks for watching, and I'll see you in the next one. Small, fast, and deadly accurate, a bullet is one of the most precisely engineered pieces of hardware on Earth. Behind every round lies a combination of chemistry, metallurgy, and engineering, all executed under tightly controlled conditions where even a microscopic flaw could mean failure. In this video, we go inside one of the most secure and advanced ammunition manufacturing facilities on the planet to uncover the step-by-step process of creating a modern bullet. From raw materials to final packaging, from sheets of brass and powdered chemicals to high-speed robotics and rigorous ballistic testing, you're about to discover how firepower is forged with surgical precision. This is not just about metal and machinery, it's about safety, control, and trust. Because when a bullet is fired, there's no second chance. Coming up, what materials go into a bullet and why each component is critical to performance. Before any bullet is assembled, it begins as a collection of raw materials, each selected with scientific precision for its role in creating power, control, and reliability. At the heart of every cartridge is the casing, typically made from brass. This golden-hued alloy of copper and zinc is prized not just for its durability and corrosion resistance, but for its ability to expand and contract predictably under pressure. When a bullet is fired, the brass casing expands tightly against the chamber walls, forming a perfect seal to prevent gas leakage, then cools and contracts, allowing it to be ejected cleanly. Massive rolls of brass sheet arrive at the factory, inspected for microscopic flaws before being fed into forming machines. But the casing is only the beginning. At its base lies the primer, a small metal cup containing an explosive compound that is sensitive to impact. When struck by a firing pin, this tiny component ignites instantly, creating the initial spark needed to activate the propellant. Because of its volatility, primer manufacturing takes place in specialized environments, often under robotic control to ensure maximum safety. Workers in this section wear anti-static suits, and the process is monitored with precision cameras to detect even the slightest error. Once the primer does its job, the fire moves to the propellant, a refined chemical mixture packed tightly into the casing. Today's bullets no longer use traditional black powder. Instead, they rely on modern smokeless powder, typically made from nitrocellulose and various stabilizers. This powder burns cleanly, reducing smoke and residue, and can be tailored for specific ballistic profiles. Every grain of powder is measured with incredible accuracy, because even a slight deviation could alter performance or, in extreme cases, cause catastrophic failure. Finally, there's the projectile, the bullet itself. Usually, it starts as a lead core for weight and density, then gets wrapped in a copper or brass jacket to increase durability, reduce fouling, and enhance aerodynamic stability. These jackets are drawn from copper sheets, shaped with high pressure, and bonded tightly to the lead inside. Depending on the intended use, bullets might be shaped for expansion, penetration, or accuracy, ranging from full metal jackets to hollow points and even armor-piercing variants. Regardless of the design, they all share a common goal: delivering force with precision. Each of these components, brass, primer, powder, and projectile, is engineered independently, but they must work in perfect harmony. Together, they form the anatomy of a modern bullet: a miniature explosion chamber, a propulsion system, and a precision-guided point of impact. The journey of a bullet begins with a simple disc of brass, cold, flat, and unassuming. But in the factory, this raw material is transformed into a critical component through a process that requires extreme force, heat, and precision. The first step is known as cupping, where brass sheets are punched into small circular blanks. These blanks are then pressed into shallow cups through a powerful drawing machine. From here, the cups undergo multiple stages of drawing and annealing, a process that gradually stretches the brass into long, narrow cylinders while carefully applying heat to prevent cracking. Annealing softens the metal just enough to keep it ductile, flexible but strong. Each casing is trimmed to exact length and passed through a washing station that removes residue and oils. They emerge clean, golden, and perfectly smooth. But they're far from finished. At this stage, each casing is run through a series of progressive dies that shape the neck and mouth, form the base, and create the primer pocket with tight tolerances measured in microns. To ensure reliability, every casing is subjected to automated visual inspection. High-speed cameras check for dents, deformities, and thickness irregularities, rejecting any imperfection without hesitation. Only flawless cases move forward. Despite the rapid pace of production, the standards remain unforgiving. A single crack or off-center primer pocket can lead to failure in the field, something no soldier, officer, or sport shooter can afford. By the end of the process, that thin piece of brass has become a highly engineered pressure vessel, strong enough to contain an explosion, yet light enough for rapid cycling in modern firearms. While the casing forms the body of the cartridge, the projectile, commonly called the bullet, is the part that truly defines its purpose. It's the piece that flies downrange, pierces targets, and delivers impact. Crafting it requires a delicate balance of weight, shape, and durability, all shaped through fire, pressure, and science. The core of most bullets begins with lead, prized for its density and malleability. Solid lead ingots are fed into industrial furnaces, where they're melted down into liquid form. This molten metal is then poured into molds or extruded into long wires, which are later cut into small cylindrical pieces, each precisely measured by weight. These lead slugs will become the heart of the bullet. But a soft lead core on its own wouldn't survive the velocity or friction of modern firearms. That's where the jacket comes in, a thin layer of harder metal, usually copper or a copper alloy, designed to encase the lead and protect it during its journey through the barrel. Sheets of copper are cut into discs and drawn through a series of dies, forming cup-like shells that will wrap around the lead cores. Once the jacket and core are prepared, the two are pressed together in a process called swaging. Under massive hydraulic pressure, the lead fills the jacket cavity, and the entire assembly is reshaped into its final aerodynamic form. At this stage, the bullet's nose profile, weight, and dimensions are carefully controlled to match its specific purpose, whether it's for target practice, hunting, law enforcement, or military use. Different designs call for different levels of complexity. A full metal jacket, FMJ, offers smooth feeding and deep penetration, while hollow points are engineered to expand upon impact, increasing stopping power. Armor-piercing bullets may incorporate hardened steel or tungsten cores, offering enhanced penetration for specialized missions. Every bullet must be nearly perfect. Even the slightest deviation in weight or symmetry can affect accuracy. That's why each batch is spot-checked using digital scales, micrometers, and profile gauges. Precision is paramount. By the time the process is complete, what began as soft lead and flat copper has been transformed into a high-speed projectile capable of withstanding extreme pressure, rapid acceleration, and precise trajectory, all in a fraction of a second. Now that the brass casing has been precision-formed and the projectile expertly shaped, it's time for the most critical stage of all: assembly. This is where the bullet becomes a complete cartridge, a self-contained unit of power, accuracy, and engineering excellence. The process begins with the primer. These tiny but essential components arrive from a separate, secure part of the facility where they've been manufactured under tightly controlled conditions. In the assembly line, robotic arms carefully insert each primer into the casing's base. The fit must be snug, tight enough to hold during recoil, yet precise enough to detonate reliably when struck by a firing pin. Next comes the propellant, a precisely measured dose of smokeless powder. Automated powder dispensers ensure that each casing receives the exact amount required, down to the grain. Too little, and the bullet might not leave the barrel. Too much, and it could cause dangerous overpressure. The powder is funneled into the casing and leveled using vibration and air jets to ensure consistency. Then the projectile, the bullet itself, is seated into the open mouth of the casing. This step demands millimeter-perfect accuracy. The bullet must be pressed to the correct depth and aligned with the casing's axis. A process known as crimping follows, where the casing mouth is slightly rolled or pressed inward to lock the bullet in place. This not only secures the bullet during handling and transport, but also helps control pressure when the cartridge is fired. Throughout this stage, sensors and cameras monitor every step. Machines verify seating depth, crimp tension, and powder levels using real-time imaging and weight checks. If any cartridge falls outside of the strict tolerances, it's automatically rejected and flagged for inspection. The speed is staggering. Modern facilities can assemble thousands of rounds per hour. But despite the volume, quality is never compromised. Each machine is calibrated daily. Operators inspect samples from every batch, measuring bullet runout, neck tension, and even chamber pressure using advanced diagnostic tools. Different calibers, such as 9mm, 5.56 NATO, or 308 Winchester, require unique adjustments to tooling and timing. The machinery adapts quickly, thanks to computerized control systems that store profiles for each ammunition type. By the end of the assembly line, what started as separate components, brass, primer, powder, and bullet, has become a powerful, precision-engineered cartridge, ready for use in everything from sport shooting to military operations. Each round is identical in weight, shape, and performance. It's not just ammunition, it's consistency made real, one round at a time. Before any bullet reaches the market, it must pass a series of rigorous quality checks. In an industry where precision can mean the difference between success and failure, every round is scrutinized for perfection. Automated systems, equipped with high-speed cameras and laser sensors, scan each cartridge for defects, checking bullet alignment, primer depth, casing length, and overall dimensions. Any slight irregularity results in immediate rejection. From each production batch, random samples are pulled for deeper analysis. Cartridges are weighed to detect inconsistencies in powder charge or material. Selected rounds are then fired in secure indoor test ranges, where sensors measure muzzle velocity, chamber pressure, and accuracy. Some samples also undergo environmental testing, being subjected to extreme heat, cold, and vibration before firing, ensuring reliability in any condition. In high-grade military or defense ammunition, additional inspections like X-rays and concentricity tests are performed. Every accepted round is tagged with a production code, for full traceability, ensuring any issue can be tracked back to its origin. At the end of this process, only the most reliable, consistent, and precise cartridges move on to packaging. Because in the world of ammunition, performance isn't just expected, it's guaranteed. Once each round has passed inspection, it's time for packaging, the final step before these precision-engineered cartridges leave the factory. Ammunition is sorted by caliber and application, civilian, military, or law enforcement. Each type follows a specific packaging protocol, designed for both protection and identification. Rows of completed cartridges are automatically counted and stacked into trays using robotic arms. From there, they're sealed in moisture-resistant boxes, often with desiccants added to prevent corrosion. Labels detail everything: caliber, grain weight, lot number, and intended use. Military-grade ammunition may be packed into weatherproof steel cans with additional shock protection, while commercial rounds are often boxed in cardboard and shrink-wrapped for retail shelves. Large shipments are palletized, shrink-wrapped, and logged into secure inventory systems before transport. Every movement is tracked, because security doesn't end at the factory gate. Ammunition manufacturing is one of the most tightly regulated industries in the world. Every aspect, from chemical storage to worker safety and waste disposal, is governed by national and international standards. Factories operate under constant surveillance, with restricted access zones, blast-resistant rooms, and real-time environmental monitoring. Employees undergo extensive training and follow strict protocols when handling sensitive materials like primer compounds or powder. Compliance with laws like the US ATF regulations, NATO standards, or ISO certifications isn't optional, it's foundational. From chemical handling to explosive limits per room, every guideline exists to prevent disaster and ensure consistent quality. Moreover, responsible manufacturers invest in sustainability, recycling spent brass, filtering air emissions, and neutralizing chemical byproducts. The goal is not just safety, but long-term stewardship. It's a product built not just to perform, but to be trusted. Whether used by a police officer in a life-or-death moment, a soldier on deployment, or a competitive marksman chasing perfection, that bullet must do exactly what it's designed to, every single time. And it all begins here, in factories you'll likely never see, operated by people whose names you'll never know, working behind the scenes to ensure that when the trigger's pulled, everything works exactly as it should. If you enjoyed this behind-the-scenes look into the world of precision engineering, don't forget to like, share, and subscribe to our channel. We bring you deep dives into how the world's most complex products are made, from factory floors to final form. Hit the bell icon so you never miss a story that turns metal, fire, and science into power. Thanks for watching, and stay curious.